Welcome to Frost and Sullivan's Growth Podcast. In this episode, we examine how integrated photonics is moving deeper into AI computing, semiconductor architectures, and intelligent sensing. As AI workloads scale, the movement of data between processors, memory, accelerators, and networks is becoming a critical infrastructure challenge. Conventional electrical interconnects are increasingly constrained by bandwidth, latency, signal loss, and power consumption. Integrated photonics offers another pathway. Optical I/O, co-packaged optics, photonic integrated circuits, and advanced packaging are bringing optical connectivity closer to compute. At the same time, photonic sensing is expanding opportunities across mobility, healthcare, manufacturing, aerospace, and defense, and autonomous systems. The opportunity is significant, but commercial success will depend on how effectively the industry can solve the manufacturing, packaging, integration, and ecosystem challenges that come with it. Let's examine where integrated photonics is heading next. AI has a data movement problem. AI computing is scaling at extraordinary speed. Larger models and increasingly complex workloads require huge volumes of data to move continuously between processors, accelerators, memory, and networking infrastructure. And that is exposing the limitations of electrical connectivity. As bandwidth requirements rise, copper-based interconnects face growing challenges around signal loss, latency, noise, and energy consumption. Photonics changes the equation by using light to move data. Optical connectivity can support higher throughput while reducing some of the power and signal integrity constraints associated with electrical interconnects. For AI infrastructure, this makes data movement increasingly important to overall computing performance. The next generation of AI systems will therefore depend on advances in processors and accelerators alongside the architectures connecting them.
Photonics is moving inside the compute architecture. This brings us to one of the most important shifts underway. Photonics is moving progressively closer to processors, accelerators, switches, and memory. Optical I/O allows large volumes of data to move between computing components using optical connections. Co-packaged optics takes this further by bringing optical engines closer to switching and computing silicon, reducing the distance that high-speed electrical signals need to travel. Advanced packaging technologies, including 3D integration and silicon interposers, are enabling even tighter integration between electronics, photonics, memory, and compute. Longer term, the relationship could become even deeper. Photonic AI accelerators are exploring the use of optical interference, modulation, and wavelength multiplexing to perform highly parallel matrix and tensor operations. Neuromorphic photonics is examining brain-inspired computing architectures, while quantum photonics is advancing across quantum computing, communications, and high-precision sensing. Photonics is therefore beginning to influence both how data moves and how it could eventually be processed.
The opportunity extends well beyond data centers. Integrated photonics has another important growth pathway: intelligent sensing. Photonic technologies can capture highly precise spatial, environmental, biological, and chemical information. LiDAR, SPAD imaging, and machine vision are improving depth sensing, recognition, tracking, and spatial perception. Fiber optic and environmental photonic sensors can provide distributed monitoring across factories, pipelines, infrastructure, and power networks. Optical biosensors and spectroscopy are expanding possibilities across diagnostics, molecular analysis, and healthcare monitoring. But sensing alone is only part of the story. Combine photonics with sensor fusion and edge AI, and these inputs can become real-time decisions for detection, classification, navigation, and automated response. This convergence creates a much broader opportunity for integrated photonics across autonomous systems, healthcare, manufacturing, mobility, and infrastructure.
Commercialization will be won in manufacturing and packaging. Technical performance alone will not determine how quickly integrated photonics scales. Manufacturing is becoming one of the industry's defining challenges. Variations in defects can significantly affect photonic integrated circuit performance and production yield. Integrating lasers, electronics, photonic components, and different material platforms adds further complexity. Packaging presents its own difficulties. Precise optical alignment and fiber coupling make photonic packaging and testing considerably more demanding than conventional electronic systems. The industry is responding with wafer-level optical testing, automated fiber alignment, digital twins, and AI-assisted yield optimization. These developments matter because integrated photonics ultimately needs to move from technically impressive prototypes toward repeatable, cost-efficient production. The companies that solve manufacturing, testing, thermal management, packaging, and heterogeneous integration could therefore capture a significant share of the value created as photonics scales.
The next phase will be an ecosystem play. Integrated photonics is also becoming increasingly difficult to commercialize in isolation. Photonic integrated circuits need to work within semiconductor manufacturing and advanced packaging ecosystems. Optical connectivity needs to integrate with rapidly evolving AI compute and networking architectures. Intelligent photonic sensors need AI platforms capable of interpreting and acting on the information they capture. That brings together chip makers, foundries, photonics developers, optical component suppliers, packaging specialists, hyperscalers, AI companies, and end users. Collaboration across this ecosystem can accelerate qualification, manufacturing, integration, and commercial deployment. And this could ultimately determine how quickly integrated photonics progresses from specialized applications toward broader adoption. The growth opportunity spans the entire value chain, from materials and devices through fabrication, packaging, system integration, and application-specific solutions. Thanks for joining us on Frost & Sullivan's Growth Podcast. Integrated photonics is moving toward a broader role across AI computing, semiconductor architectures, and intelligent sensing. As optical I/O, co-packaged optics, photonic integrated circuits, advanced packaging, and AI-enabled sensing mature, the next challenge will be translating technical advances into scalable manufacturing and commercially deployable systems. For access to our research, competitive benchmarking, and best practice frameworks, head over to frost.com or email hello@frost.com. We'll be back soon with more to help you stay clear-headed and growth-ready.